good person.
Yes.
Technologically aware.
And if it happens to result in a dinner date, like, all the better. All right, let's see here.
Can I go out with that girl?
Eagle Girl, 1131301.
All right.
On the YouTube videos.
Before I have to edit this video, let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and I thank you for most of these students. Help us to glorify you what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so.
Don't you thank God for?
I didn't. I said what I said. Let's see here. So, lecture 17, algebraic field extensions. So let's get right to it. And so technically, this is section 13.2 in Dummett and Foote. Yes, as one of you asked me to post the PDF for lecture 16, a very reasonable request. I have written it out. I do intend to post it, hopefully soon. And maybe we'll even look at that at the end of class. All right. There's really not much there besides section 13.1. So here we go. Definition. Let K over F be an extension field. The element alpha in K is said to be algebraic over F if alpha is a root of a non-zero f of x in f of x, period. If alpha is not algebraic, over f, then alpha is transcendental. Over f. The extension K over f is said to be algebraic, all right, if every element of K is algebraic over F. All right. So this is what we mean by algebraic extension.
Quiet. Can you just drop it? It is. I would agree with this one.
Dr. Cook gets easily distracted.
That's true.
Can you yell at her? You're not very good at yelling.
Well, no, actually, you showed the opposite.
Yar, stop. All right. Okay, so proposition Proposition 9, all right, it says that if alpha, well, let me try to state it properly. Alpha algebraic over F, then there exists a unique monic irreducible polynomial which has alpha as a root, all right. If alpha is algebraic over F, then there exists a unique monic irreducible m sub alpha f of x in f of x such that m alpha comma f of alpha equals to 0. All right. In other words, there exists a unique polynomial of lowest order which, when you evaluate at alpha, you get 0. Not saying, of course, that alpha is in F. That's kind of the point here. All right? So furthermore, if f of x is a polynomial with coefficients in f such that f of alpha is equal to 0, then the minimal polynomial, m alpha comma f of x, divides f of x. Oh, yeah, by the way, definition, this uniquely existent monic irreducible polynomial is the minimal polynomial of alpha. M sub alpha comma f of x is the minimal polynomial of alpha over f. How do you think we are gonna, how would you prove this, do you think? What's that?
You just like construct it, like would it just be like a constant one?
Yeah, let's try to discover the proof together. How about that? Proof. So we have that alpha is algebraic over f. What's that give us? It's the root of a non-zero f of x, right? So we could say, so there exists f of x, a polynomial over f, right? Non-zero, such that f of alpha is equal to 0, right? So then, I think the laziest way to do this is to consider the ideal generated by f of x, right, is an ideal of the PID f of x, right? And what did we know about, how do we, what's the generator for that ideal?
Polynomial of least degree in there.
Polynomial of least degree in here. You know, let f of x be generated by, let's say, m of x, where m of x is the polynomial of least degree in f of x with leading coefficient 1, right? What did this term monic mean? Did you guys understand that? Monic means the leading coefficient's 1, right? So so in principle, of course, there's infinitely many choices for the generator of this ideal, right? But if we force the leading coefficient of the generator to be 1, then there's just one choice, right? And then I think it then should be obvious that this m of x has to divide f of x, right? Because this is all this is all multiples of f of x, right? But if that ideal is given by all multiples of m of x, of course, then that means that m of x has to divide. Anyway, m of x has to divide f of x, of course. All right, so, this is, I would say this is not a proof at the moment. This is kind of more of a proof sketch, right? But I think that's sufficient for the moment. All right. I'd really like us to look at, so like, there's a better proof, of course, on page 520 of Dummett and Foote. And I think if you look at that, what you're going to find is it's just basically using the division algorithm to like rediscover this theorem that we're just quoting, right? Which is essentially that there's a minimal polynomial of least degree which generates that ideal. That's what's really at heart here. Okay, so so let's see here. Definition: given alpha algebraic over F, the unique monic irreducible m sub alpha f of x, which is a polynomial in F, right, is called the minimal polynomial. All right, minimal polynomial of alpha over F. Moreover, the degree of alpha is equal to the degree of m alpha comma f over x. And as you might suspect, we get tired of writing m sub alpha comma f, right? And so given proper context, we might just say m of x, or we might even just say, m sub alpha of x, all right? But this notation is helpful, especially while we're getting used to it. So Violet's still in her note-taking.
I lost my iPad.
You lost your iPad.
So there's this thing called paper.
There is. I think I might have. I might have some paper.
Believe it or not, I actually have an extra notebook.
You have a lot. Shane's got a lot of
I
paper.
too have printer paper. See, she's in her emo phase.
Yeah, her emo face. I'm not sure what that means, but
Even with people with a lot of black eyeshadow.
a lot of black.
That's the only requirement.
The only requirement is a lot of black eyeshadow and black lipstick. Ew. Oh, I don't really like that. Let's see here. Do you? Okay, so C is an extension field of the reals, right? And in fact, alpha equal to the imaginary number I, right, is algebraic over R, and in fact also C. In fact, that's part of a larger trend. If you have a number, an element which is listen to me. If you have a number which is algebraic over a field, it will also be algebraic over any extension field of said field. All right? So you have this to look forward to. But if we look at m sub alpha comma R, well, what's the unique monic polynomial of least degree which takes this as a 0? Like that's, if we get into the mechanics of the proof that I've partly butchered today, but it's all your fault. No, I'm just kidding. It's my fault. I'm just saying, like, this is okay, but I think we can improve. We can improve that. So it feels like there's something missing, is what I'm saying. But anyway, so the unique monic polynomial of least degree, which takes I as a 0, is what? X squared plus 1, right? That, of course, is an element of the polynomials over R. Okay? And so what we find is that the degree of I is equal to 2 over the reals. However, the minimal polynomial of alpha, which is I here, over the complexes is just x minus I. That is a polynomial which was not available to us with real coefficients, but it is available to us if we're dealing with complex coefficients. And that tells me that the degree of I is equal to 1 over the complex numbers. And this is kind of like, general dumb theorem. If alpha is an element of the field, then the degree of alpha is equal to 1 over the field. It is so true. And the proof of this theorem which is the kind of theorem I have the mental energy to prove today, is this. M sub alpha, comma f of x is x minus alpha. Check it out. That is a monic polynomial. You definitely can't have lower degree than that. And it takes alpha as a 0, right? Therefore, alpha has degree 1. And you can prove that that's irreducible. Yes, sir?
Is that an if and only?
Is that an if and only if? Well, yeah, I think so, actually. Because if we do converse to dumb would be, suppose, you know, you have m alpha f of x is equal to x minus b, right? Where m alpha f of alpha is equal to 0. In other words, assume that it has a minimal polynomial of degree 1. It has to be monic, so that's why we have x. I mean, I could say x plus b if you like, whatever. But that's all that you got in the case of degree 1, irreducible, you know, linear polynomial. That's it, right? Monic. And if we're assuming the converse, which is to say that alpha has degree 1, which means that that's its minimal polynomial, and of course, by definition, is that, well, then what? You've got alpha plus b is equal to 0, which tells us, of course, that b is equal to, not surprisingly, minus alpha. But what's our assumption here is that m of f comma x is an element of the polynomials over f. Hence, alpha equals to minus b, if you like, is an element of f. See, before you had asked that question, it would have been a nice test question. But now you've asked it, so you've exposed the... It would still make a nice test question? All right, well. You'll forget? You will.
I wonder why.
All right. So another proposition, which I won't prove because it's like, I'm just going to talk about the proof because I think the proof is kind of obvious. Let alpha be algebraic over f, all right? And let f of alpha be the field generated by alpha over f, right? We talked about that last time. A simple extension, right? The field which is containing f and alpha. All right. Then f of alpha is isomorphic to f of x mod what ideal? What's that?
The ideal generated by the...
Which? I'm looking for a polynomial here.
Oh, sorry. M alpha.
M alpha, right. X minus alpha would be a legitimate answer in the case that f was an element of the field, in which case this whole silly thing would collapse back down to f again. And, you know, that's a possibility, right? If, indeed, if m is in fact just x minus alpha, then the polynomial quotient just squashes down to the constant terms, which shows you, of course, what we, well, the dumb case of this example, but there you go. Yeah. Moreover, if we look at the degree of alpha over f is equal to what? The degree of the extension of the field by alpha over f is what? It's equal to what we have defined to be the degree of alpha, right? And of course, I mean, you might say degree sub f of alpha if you're worried about the ambiguity there. Because of course, degree of an element, it depends on what we take as our base field, right?
Yeah.
All right, so some examples.
Bless you.
I don't know what's going on here.
Packing up a lung back there.
All right, let me continue with some examples here. So so generally speaking here, guys, I'm kind of torn between two competing priorities. The one is showing you examples. The other is showing you like careful proofs, right? So in the interest of doing both, it's best if I have written out some proofs that I can project and talk through, right? But I think it's also good for us to work some out kind of step by step. But there's not always time for both, obviously. So what's best, of course, is if I actually have them written out so we can look at them on the projector. But sadly, that is not the case today. Well, it's almost not the case. We'll see. Example 2. If we have alpha equal to the square root of 2, but I want to do some examples. That's my point. Alpha equals square root of 2. If we look at the minimal polynomial of the square root of 2 over the rational numbers, well, that's just x squared minus 2, right? And so the degree of the square root of 2 is 2. All right. And of course, this is over q, obviously, right? Example 3, if you take alpha equals to the square root of 67, then guess what? The minimal polynomial of the square root of 67 is just x squared minus 67. And of course, that is a rational polynomial. And so, lo and behold, the degree of the square root of 67 is 2. In fact, you see this has really nothing to do with 2 or 67, right? Any prime, the square root of any prime gives us a degree 2 extension over the rationals. Yes? Example 4, if we looked at alpha equal to the nth root of 2, then we could use the minimal polynomial of the nth root of 2, x to the n minus 2 as a rational polynomial. And that would tell me that the degree of the nth root of 2 is n. Right? In contrast, if I look at the minimal polynomial of the nth root of 2 with respect to the reals, what's my minimal polynomial? Yes, x minus the nth root of 2. Very silly, but there it is. Because that is a polynomial with real coefficients, which is monic and of least degree, which takes the nth root of 2 as its 0. Oh,
So silly.
it is silly.
I blame Jacob.
It's the sad thing is, like, I could give a really good argument. It could be clear and nice, even beautiful, and there would be no enjoyment. But if I make a mistake, then I've given the audience what they yearn for. An opportunity to mock. Bad people, I'd say. All right, so here, you know who you are. The mocking has reached hiccup levels. Let's see here.
Wait, is that degree 1?
What's that? Yes, this, so here we go. If we take the reals, adjoin the nth root of 2 over the reals, the degree of that versus the rationals, adjoin the nth root of 2 over the rationals. So according to the proposition we just wrote, what is the degree of these extensions? Well, this is a very silly extension because it's a degree 1 extension, which is just a fancy way of saying that this and that are the same stupid thing. All right? In other words, but this on the other hand, these are not the same. And in fact, this is a degree n extension, right? So if I was to say theta equals to the nth root of 2, for the sake of my writing, we could say q adjoin, the nth root of 2 is, in fact, like the rational span of 1 theta. This is the writing I'm talking about. Theta squared, theta cubed, theta to the n minus 1, which of course is the nth root of 2 raised to the n minus 1 power, which is the kind of thing I've been writing had I not introduced the theta. Ugh. It is an n-dimensional rational space, rational vector space. That's what the degree n extension is. Yeah? All right, so all of the examples I just gave you guys, why is it that we had irreducible? Why are these irreducible? I mean, I just said, I claimed they were. I didn't explain why. Can you explain why? It's the same reason, every single one. Well, ignoring the linear one, which is just dumb. We proved that any linear polynomial is irreducible. What's the criteria? Not Einstein, but Eisenstein. Eisenstein, all Eisenstein, all around. Eisenstein with p equals to 2, Eisenstein with p equals to 67, Eisenstein with p equals to 2 again. Eisenstein gives us irreducibility of every last one of these. Because every non-leading coefficient is divisible by the prime, but not divisible by the prime squared. In the constant coefficient, constant term, which is all there is not divisible by 2 squared, not divisible by 67 squared, not divisible by 2 squared. All right, so Eisenstein is the answer. All right, so let us look at another example. Aw, man. Come on. So up till now, we've focused on simple extensions, right? So these have been extensions which were just, there's some primitive element, and so it's just like what we just did there with theta, and we could just look at it as q extend by adjoining the nth root of 2 and then everything that generates, right? So, but it's a simple extension. It's f adjoin alpha, right? But not every extension looks like that, right? It's a generally like, this is a somewhat more technical question, which is like when you have an extension which isn't manifestly simple, when is it possible to rewrite it as a simple extension? That's a challenging question. I don't know if I know the answer to it right off the top of my head, actually. Which isn't to say that there is an easy answer. It's just to say I haven't reminded myself the answer. But let's see, what example am I on? 5? Oh, 5, okay. So, example 5. What's that?
I got off.
6?
No, I think it's a me problem.
It's a u problem. Okay. F of x equals x to the 4th minus 5x squared plus 6. All right? So we can look at this. This is a polynomial over the rationals, right? It's certainly not irreducible, right? So let's see here. We can factor this, though. This is what? X squared minus 2 times x squared minus 3, right? Well, and then, so this is a product of irreducibles, isn't it? the irreducible x squared minus 2 and x squared minus 3, which are irreducible by what? Eisenstein, very good. Ha, finally. All right. So then, if we look at, let's just to avoid some
You missed it. He took a big drink, he said.
Okay. All right, then. Let's see here. I say we can form, so here's, I got a couple calculations here. We can look at Q of x mod the ideal generated by x squared minus 2 and rationals Q. Thank you. And in which, let's say alpha equals to x plus the ideal generated by x squared minus 2, right, has alpha squared minus 2 equals to 0, right? And we could also look at, we could look at Q of x mod x squared minus 3, in which beta equal to x plus the ideal generated by x squared minus 3 has beta squared minus 3 equals to 0, right? Okay, so we have a couple different equations we can write. One of them is this: f of x is equal to x plus alpha times x minus alpha times x squared minus 3. All right. And this makes f of x manifestly an element of Q adjoin alpha. It's like a polynomial in Q adjoin alpha, right? You can multiply this out to make that explicit. I think it's clear though, right? If you multiply this out, you just got rational numbers and alpha, right? It's a polynomial in that. On the other hand, you could look at this as x squared minus 2 times x plus a beta, x minus beta, right? So in that sense, f of x is a polynomial in Q adjoin beta over x. And then I said, since Q alpha is a field, we can form, this one's a little funky, let's see here. So we can also look at Q alpha polynomials in that. I'm going to introduce a t and quotient that by t squared minus 3. Then this suggests I get beta equals to t plus t squared minus 3. And in there, I get f of t is t plus alpha, t minus alpha, t plus beta, t minus beta.
Is this the same alpha and betas?
If you want, we could use a different letter here, like T bar. I think conceptually, no, they're not the same.
What?
was the problem?
What?
No, we're saying alpha.
Alpha and beta are the...
Oh, yeah, same alpha beta.
Okay.
Yeah.
Wait, it's not the same T?
Well,
I think we used T.
Yeah.
Anyway, so here Q alpha beta is smallest extension field of Q containing alpha and beta. All right, so what I'm trying to get at here is the idea that it's probably, I almost think, I mean, I'm just working off my old notes, guys, but like I think I'm not convinced the alpha and beta are helpful. Like, we could start with Q, right? And well, Q is the base field, all right? Q is the base field. So I'm going to start down here. Here's my Q, right? Then I can extend to Q adjoin with the square root of 2. All right? Then I can extend again to Q adjoin the square root of 2, adjoin with the square root of 3. This is also denoted simply Q adjoin square root of 2 comma square root of 3, because it turns out that looking at polynomials, well, anyway, these are the same, like, same object. So in this right here, we have everything we need, right, to completely factor f of x. Agree? So like in here, I can write f of x is x plus root 3, x minus root 3, x plus root 2, x minus root 2, right? I can do part of that here, right? Like here, I can just do what? F of x is what? You know, x plus root 2, x minus root 2, but I'm stuck. Yeah, x squared minus 3 is irreducible, actually, over this field. We haven't proved that yet, but I think we're going to be able to argue, claim, let me make a claim here, claim x squared minus 3 is irreducible over Q adjoin the square root of 2. All right. We're soon going to discover some theorems that allow us to prove this. Now, I know you guys have been wanting me to say these words, but I believe that Q adjoin the square root of 2, square root of 3 is the what for f of x? The what? Minimal? No. I mean, it might be. I mean, minimal polynomial for what, though? Okay, so I told you guys like a few minutes ago, it was sometimes not obvious that something's a simple extension. Is this a simple extension over the rationals? In other words, can I find a single element that Q adjoin that element gives me that field? Some of you say no. Yeah, okay. Now, what can you tell me about this rational polynomial, though? It does what? It completely factors over this field. That makes this the what? It has split the polynomial into its linear factors. This is the splitting field for f of x. Yeah, see? You didn't think that was going to happen, did you?
You told us it wasn't going to happen. You explicitly said it wouldn't.
I know, I lied. Sorry.
He says, I don't know how to work on that.
We can totally do that problem.
Yeah, it's now we'll talk about that more systematically in a future lecture, of course. But all right. So let me work on the big theorem for today. So I think the answer to the question, though, that is actually a simple extension, but it's not at all obvious what the alpha, like Q adjoin what alpha? And I don't think 6 is going to be it, though, because I don't think there's any way you can use 6 to... Is it 6? I don't... The square root of 6? I guess the question is, how do I get from square root of 6 to like... The question is, how do you get from square root of 6 to like the square root of 2? Like, how do you get from here to there? Because this field has the square root of 2 in it, right? So if you're using square root of 6, Q adjoin square root of 6, this is things of the form a plus b root 6, where a and b are rational. Now it is clear to me, you're right, that if your field has square root of 2 and square root of 3 in it, it has a square root of 6. That is true. But it is not obvious to me that the other way around is the case. So I'm just going to leave that sitting there as something to think about. It's not, I don't think it's a trivial matter. All right, so the following theorem is very nice. And, did I print the wrong lecture out? Well, that's just par for the course today. All right, so I'm going to have to try to do it from scratch. Theorem. Let F extend to L, and let L extend to K, where, let's say, the degree of F over L, my bad, other way around, right? The degree of L over F, F's the base field here, is equal to M, and the degree of K over L is equal to N. Then the degree of K over F is simply equal to K over L times L over F, or if you like, M times N. In other words, if we have two finite extensions, one after the other, all right? So the picture is like this, K, L, F. And usually people might put like they might adorn these vertical lines with the appropriate like dimensional labels. So this is like a degree M extension, a degree N extension. Then to go from here to here, you've got an MN extension, all right? And the proof of this is actually, it's quite nice. It just requires a little bit of attention to notation. So to calculate the extension, the degree of an extension is basically to find a basis, all right? So like the proof goes like this. We're given, let's say beta equal to v1, v2, v sub m, a basis, and well, it's an F basis for L. Okay. And we're also given gamma, which let's say it's I don't know. Where was I? L. So let's say L1, L2, LM, oh, not M, but N. N is in nanu nanu. And an L basis, right, for K. So L is a vector space over F. K is a vector space over L. Then I'm going to argue that if we do upsilon equal to like VI Lj, such that 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N, serves as F basis for K. So there are two things we need to prove to show that it's actually a basis, right? We need to show spanning and linear independence. So let's let, for lack of an imagination, I'll say X be an element of K, which is equal to the span of gamma, which implies then that X is equal to the sum over what? J equals 1 to N of, let's say, X sub J, L sub J. Do we agree? Where, what are the X sub J's? So I should, to be clear, this is an L span, right? Where X sub J is an element of L for J equals to 1 to N. So that's what it means for gamma to be an L basis for K, right? But then what? Well, X sub J is an element of L, which is the span over the F basis of beta, which tells me that X sub J is equal to the sum over I equals 1 to M of, let me call it C sub Ji of V sub I, where C sub Ji are elements of F for I less than or equal to, good grief, 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N. Right? Thus, X is equal to the sum J equals 1 to N, the sum I equals 1 to M of C, J, I, V, I. And I seem to have lost something. Right, LJ. Thank you very much. That is an element of the span over the F field of upsilon. See, because the CJIs are F elements, right? And yeah, well, that's upsilon. Yeah. So it's a spanning set. What do we need now? Linear independence. So let us suppose that, why reinvent the wheel? We already got notation in front of us. So J equals 1 to M, and some I equals to 1 to M of CJI VILJ is equal to 0. So look at that. Behold, we have that in red parentheses is equal to 0. What's that mean then? The sum I equals 1 to M of CJI VI is equal to 0 for J equals to 1 to ... n by linear independence of what? Fill in the blank for me.
Yeah.
Gamma. Very good. Which then implies that Cji is equal to 0 for all 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n by linear independence of beta. Right? Consequently, upsilon is a basis for K as an F vector space. And counting finishes the job, right? Because there's m times n things in the upsilon basis. What do you guys think? You don't like it? I have put this on many a test because I think this is actually a nice proof that actually you can, once you understand this proof, you just have to choose notation and it just all falls together. Okay, so if we go back to this over here, right? If you go back to this over here, what is the dimension? This is like degree 2. This is also degree 2. I'm alleging, right? That I only know that's degree 2 if I actually have, irreducibility of that polynomial I'm claiming, right? Maybe that's kind of the idea there. Let's see here. Well, thoughts are not entirely clear on this point yet. We'll come back to this. There's a way to use this paired with the fact that this is clearly 2, and you can actually give independent arguments to establish that the dimension of this is 4 over q. If this is degree 4 over q, if the degree of this extension is 4 over q and the degree of this is 2 over q, it forces the degree of this extension to be 2, which then implies the irreducibility of that polynomial. So there are ways to prove irreducibility of polynomials by sort of these circuitous arguments. I think that's really just a theorem. There's a theorem in section 13.2, which we'll probably do like next time, I guess. So can you guys just, one other thing for today, and then I'll shut up. But what's the degree of like pi over q? We haven't defined it, is the answer. See, we've only defined the degree of algebraic elements, right? So pi is transcendental over q, right? What does that mean? If you had, p of x equals, say, a sub 0 plus a1x plus a sub 2x squared plus dot 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 plus an, well, plus x to the n, I guess we're doing monic, yeah? Is there any polynomial of any degree that you could construct which would take pi as a 0? Like, can you, is it possible to do a0 plus like a1 pi plus a2 pi squared plus dot 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 plus pi to the n equals to 0? Does such a, p of x with rational coefficients exist? So the answer to this question is no. but I'm not going to prove that in here. That is nasty. All right, that's actually not an easy thing to prove. But one of the characterizations you could give is that Q adjoin pi, well, not adjoin pi, but let's say, okay, well, here's the thing. Q adjoin pi is the smallest field which has rational numbers and pi with an inverse. So that's actually like isomorphic to rational functions over, like this being f of x over g of x such that f of x and g of x are polynomials in Q with, you know the deal, g of x not equal to 0, right? If I was to say Q adjoin pi, which would not mean the field, right? This would just mean the smallest ring, all right? The smallest ring which includes Q and an element pi. This is actually isomorphic to polynomials. Because there's no way you can quotient pi to 0 with some polynomial ideal. So anyway, these are just some fun things. But anyway, more on field extensions next time. And I guess I should show you guys. I tell you what, rather than showing you, I'll just post it for you.